Hey guys, Bots1925 here, and today I'll be watching this, or recording it. I'm just gonna put the microphones on.
Slowly drive the box out, and then once it's free, they can pull it out of the work site. I'm going to set this here for just a moment to talk to you about what the work site looks a little bit like.
So
this is one of the plastic mock-ups.
So I'm going to pause that.
But it does give you an idea of how the installation works. So when you look at the installation bracket, the blind mate connectors will be inside this bracket here. And those will mate with the ones that are on the back side of the MDM. So the MDM has mating connectors, electrical and power and data, in the back of it. The cold plate that it's mounted to is right down here, and then it has these 3 wedge locks that are at the back of it. And the way it works is when you slide the 2 together, you see there's pins that are on the ORU that go into the slots right here. There's 4 pins that'll just slide into those slots. And then as the 2 come together, the wedges that are on the cold plate interface with the wedges that are on the the bottom side of the ORU. So this is actually a wedge, and then as you put the 2 together, the 4 pins go into the slots, you put the 2 together, and then the wedges come together in the back. As you drive the bolt, when it gets to the wedges drive next to each other to put a nice preload onto the bottom of the box, so it's very firmly mated to the cold plate, so that it gets good cooling. With all the electronics in the box, there's quite a bit of heating that builds up there, and we need to make sure that it's got good thermal conductivity with the cold plate on the box.
And that was Glenda Brown on this past Friday during a press briefing, laying out all of the tasks associated with the extravehicular activity that Rick Mastracchio and Steve Swanson will perform to begin our coverage, end-to-end coverage of the EVA at 7:30 in the morning Central, 8:30 a.m. Eastern Time, and Central 8:30 a.m. Eastern Time. And they plan to begin the EVA about 8:20 Central Time, and it's scheduled right now to for a duration of about 2.5 hours. As mentioned at the top, today, April 22nd, represents Earth Day around the world, and there's no better way for us here in Mission Control to celebrate Earth Day than to have a special guest joining us for the, I guess we'd call it a celebration, and that is Dr. William Stefanoff. He is the Associate Space Station Program Scientist for Earth Observations. You're also the lead for Earth Science and Remote Sensing Unit here at the Johnson Space Center. Welcome, Will.
Thanks, Kyle.
Good to have you here. We know that for years and years that one of the tasks that the crew loves to do is look out the window, but it's a lot more important to that for the team here on the ground. But why is it so valuable to look at the Earth from the ground?
Well, it's part of a long-standing tradition of looking at our planet from space. The perspective from orbit allows us to see things that you can't really see from the ground. It also allows you to collect data that our eyes necessarily can't recognize by looking at different wavelength regions. And also it enables us to collect data over remote parts of the Earth on a very regular basis that might be impossible or difficult to get out on the ground to actually take specific samples or specimens or measurements of.
Right. So talk a little bit about the different kinds of cameras. We see Earth views all the time, obviously, but talk to us about the different kind of cameras, the sensors that are aboard the space station right now that are pointed down or looking at us here on the Earth.
Okay. But right now, I'm going to focus on the NASA sensors, although our international partners also have their own systems on board. Can I have the first slide, please? What Well, I'll start on the exterior of the station. What you're looking at right now is the Japanese experiment module and its exposed facility. And if you follow the Canadian arm at the bottom of the image out to its end, and then look pretty much straight up towards the top of the photo, you see a white box that looks like its front is cut out.
Right.
And there's a sort of a Mylar wrapped instrument package in there. Inside that instrument package sits the HICO, the hyperspectral imager for the coastal ocean. And that is a sensor that is specifically tasked, as its name suggests, on looking at oceanic processes along the coasts. It's a hyperspectral sensor, which means it looks at a large portion of the electromagnetic spectrum, broader than our own eyes can see, but it chops that spectrum up into 128 different little slices. And by looking at the energy that returns back to the sensor from the Earth's surface in each of those little slices, you can actually build image spectra. These can be thought of as fingerprints, if you will, for specific chemicals or materials on the Earth's surface. So some of the things that they've used that sensor for are, the EPA in particular has looked at water clarity and water quality, for one thing. And they've been developing apps that people can use to see what the water quality is at a particular spot that they might be, say, wanting to go to swim in or so. Next slide, please.
Anyway.
Now we're going to move inside the space station because we have sensors both exterior and interior. Here
Probably
you
not
see a picture
space rocket,
of
but why not?
former ISS Commander Chris Hadfield, and floating there in front of him is the iServe camera system, and this is the ISS Surveyor Environmental and Research Visualization System. It was specifically built to support the NASA Surveyor program, which collects data and helps developing countries develop things like maps of agriculture, respond to disasters, and things of that nature. Next slide, please. This is the iServe camera system mounted in the wharf, which is the Window Observational Research Facility. This is inside the U.S. Destiny Lab module, and it's specifically designed for remote sensing instruments to be positioned inside and look through the Destiny Lab window.
And that's a very polished window compared to
Yes.
other windows on the station,
Yeah.
right? Specifically for this type of observation.
Exactly. In fact, it's the finest optical quality window that's ever been sent up on a manned spacecraft. And what the iServe system is, it's kind of an innovative design. It's a high-end commercial off-the-shelf digital camera mated to a Cassegrain astronomer's telescope, very similar to what an amateur astronomer might buy at home. And putting those two together allows this camera system to collect very, very high-resolution data on the Earth's surface, about 3 meters per pixel. Next slide, please. Still inside, the other sensor system that we have is the Crew Earth Observations Facility. And this is the station. Astronaut photos taken with handheld digital cameras off the station windows has been collected since 2000. And here you see NASA astronaut Don Pettit in the cupola. And he actually has a dual camera system that he rigged up where he's taking infrared data with one camera and visible wavelength data with the other camera. And so all these systems put together enable the ISS to collect a wide variety of data for a number of different surface processes. We're also going to have, actually going up this year, being installed this year, 2 new sensors, the CAT system, the Cloud Aerosol Transport System, and the ISS Rapid Scat system. And what CATS will do, it's an atmospheric sensor, and what it does is uses a laser system to look at aerosol concentrations in the Earth's atmosphere, and that relates directly to climate change investigations. It provides data useful for determining how much energy is absorbed by the atmosphere and reflected back into space. The Rapid Scat system looks at the sea surface, looks at wind patterns on the sea surface, and that also gets back to looking at how, in a warming global climate, how surface circulation patterns change.
Well, now you've talked a little bit about some of the instrumentation on this station, but let's talk now about, maybe show us or talk to us about some examples of what we've learned thanks to some of those instruments on the station.
Okay. This slide, what you're seeing right now, this is a HICO scene of Galveston Bay. And fortunately, JSC is just off the edge of the image there. We're not quite there yet, but the greater Galveston Bay system. And like I mentioned earlier, this kind of data is being used by groups like the EPA, also other groups, particularly a group that I lead here at JSC, looking at regional climate change and hazard and potential sustainability issues for the center itself. This is a hyperspectral sensor, but right now you're looking at a visible camera, sort of a visible wavelength view.
Right.
So it's more intuitive to our eyes. But if you go into that each pixel on that image, you can pull out spectra that's useful for looking at things like I said, water turbidity or presence of algae, certain bacteria, different chemical constituents in plants, all things that are useful for looking at how climate reacts to different changes.
Right.
Next image, please. This is